Hello everyone, my name is Soraisobe from the University of Aichi, Japan. Today, I'd like to talk about low-bit quantization and acceleration based on bit share dot product unit with 0-bit skip. These slides show an outline of our presentation. Let me start talking about the research background. In recent years, there is a demand for edge devices applications using CNNs. However, CNNs require a lot of MAC operations. A CNN accelerator with high speed and low power consumption is strongly required for AI edge applications. Quantization of CNN parameters and activation signals are a good way to achieve high speed and low power inference. Low-bit quantization, such as 1 and 2 bits, is suitable for efficient edge AI. More than 2-bit quantization is also required to achieve sufficient recognition accuracy. BISPON is based on parallel computing using bit share dot product units that calculated two vectors dot product in a bit share manner. The BISPON supports precision scalable operations on CNNs. The BISPON can achieve a fast and energy efficient dot product of vectors where each element is quantized into 1 or 2 bits. However, the performance becomes rapidly worse as the bit width increases. It is not suitable for more than 2-bit quantization. Our objective is to realize precision scalable operations with higher performance at higher calculation precisions. We propose an extended bit share DPU that supports a 0-bit skip function called DPUZ. We evaluated the performance of DPUZ approach with low-bit quantized CNNs from 2 bits to 8 bits. Next, I'd like to explain the relationship between dot product and convolution operation and how we quantize the CNN to raw bits. Convolution operation corresponds to the dot product of filter vector and a feature map vector. For each output pixel of an output channel, we calculate convolution operation with the same filter. CNNs requires many dot product operations. We typically use 32-bit floating point for IOs and parameters when training and inferencing on the GPU or CPU. Quantizing these 32-bit IOs and parameters to 1 to 8-bit reduces the computation cost. The implementation of quantized neural network is suitable for FPGA. WRPN is a kind of quantization algorithm for neural networks. Activations are clipped to 0 to 1 and quantized into pseudo integers that corresponds to k-bit unsigned integer. Weights are clipped to -1 to 1 and quantized into pseudo integer that corresponds to k-bit signed integer. The round function causes gradient disappear, so we use Streetsville estimator to approximate gradients. We used L2 norm for the regularization algorithm. When parameters are quantized into raw bits, such as 2 and 4 bits, many parameters are rounded to 0. That results in a gradient vanishing problem. To avoid such problem, we introduced two-step training based on WRPN. In the first training to enhance propagation, we expand the distribution of the quantized parameters by scaling up each parameter with certain constant before clipping it into -1 to 1. In the second training, we removed the scaling factor and train based on the original WRPN. This training method produces low-bit and sparse filters, which dramatically increases the computational efficiency. We evaluated the accuracy of quantized ResNet 18 by two-step training approach. We use the Cipher10 dataset. The sparsity rate is the percentage of zero values for the parameter. Even when we quantized ResNet 18 into 4-bit activation and 2-bit weight, the accuracy degeneration is small, while the sparsity rate becomes 99.41%. Next, I'd like to introduce the bit serial-based dot product and its performance. In a bit serial dot product, the L-bit weight vector W is divided into binary weight vector. Similarly, the n-bit input vectors X is divided into binary inputs vectors. The dot product of W and X is calculated by LM binary dot product. For example, this figure shows the dot product of 2-bit weight vector and 2-bit input vector. We can divide the dot product to these 4 binary dot products. We can calculate the dot product in a bit serial manner in 4 clocks. The DPU is the circuit that performs bit serial dot product operations. The binary dot product is calculated by AND and pop count circuits. The length of input vectors determines the DPU input size. We implemented and evaluated the DPU circuit with Vivado and Vertex VU9 FPGA. We set the operating frequency as 200 MHz. This graph shows the lookup table utilization of DPU for each input size of DPU. The input size indicates the length of the binary vector. The increased speed of lookup table is gradually reduced as the input size increases initially. Logic utilization is almost proportional to the input size when the input size is large. As the input size increases, the performance per lookup table of DPU is improved, but the implement speed is reduced. For binary quantization, DPU is outstanding compared with 2-bit MAC. On the other hand, DPU spends LM clocks for L-bit weight and n-bit input. The performance is reduced to 1 over LM. Therefore, DPU is not suitable for than 2-bit operations. Next, I'd like to show the energy efficiency of DPU. The DPU energy efficiency is quite high for a binary dot product, and we can see the peak around an input size of 72. Next, I'd like to introduce the proposed 0-bit skipping. To reduce the latency of DPU, we introduce a 0-bit skipping technique. If the binary weight vector is 0 vector, we skip binary dot product relating to it. Combining low-bit quantization and pruning can significantly reduce the overall latency. There are 2 types of convolutional operations using DPU. The first one is a depth-wise approach, in which W corresponds to a channel of a weight tensor, and dot product is calculated channel by channel. The second one is a point-wise approach, in which W corresponds to elements of the same coordinate and of multiple channels. We employ a point-wise approach. Zero value skip ignores dot product if W is 0 vector. When W equals 1 and 0 vector, dot product operations cannot be skipped. 0-bit skip ignores binary dot products if Wi is 0 vector. When W equal 1 and 0 vector are half of binary dot product operations can be skipped. We evaluated the 0-value skip rate and 0-bit skip rate for quantized ResNet 18. The table shows the comparison of 0-value skipping rate and 0-bit skipping rate when the DPU input size is 32. The performance of DPUZ is estimated from performance of DPU and the skipping rate. The performance of DPUZ is about 15 times higher than that of DPU at 4-bit activation and 2-bit wait. 0-value skip can reduce the number of operations to 8.56%. 0-bit skip can skip addition 1.91% of the remaining operations. Let me conclude this presentation. We proposed an extended bit share DPU that supports a 0-bit skip function called DPUZ. Based on a well-quantized CNN, whose sparsity rate is high, we demonstrated that DPUZ achieved about 15 times higher performance per lookup table, and it has big potential to realize high performance. In our future work, we will implement a whole CNN accelerator of mixed precision based on DPUZ. This presentation is based on results obtained from a project commissioned by NEDO. That's all. Thank you for your kind attention.